So yeah, and so don't hesitate to interrupt with a question if you have one. Okay, so free body diagrams. The basic purpose is to understand how all the forces acting on an object, better understand how the forces acting on an object are, and that'll help us better understand how that object is behaving in space. It can also help us solve for an unknown force acting on the object if we know about other forces that are acting on it. And lastly, it can help us understand the net movement of an object if we know all the different forces acting on it. So the basic premise for a free body diagram is you want to list the forces that are present. And as you get more and more practice with physics problems, you'll get better at quickly identifying what forces matter and what forces are not going to be present in the situation. So that can be gravity, normal force, tension, friction, electrostatic force, et cetera, et cetera. Next thing to do is to set your axes. So which direction is the x-axis? Which direction is the y-axis? Is it going to be like this and like this? Is it going to be tilted, et cetera? And then also which direction is positive and which direction is negative, because this can be important when you're adding up multiple forces that are acting in the same axis. Then you look at your forces that you've listed and figure out which ones act in the x direction, which ones act in the y direction. And you can do this once you've put together your diagram, because it'll be pretty obvious for you once you look at it visually. And note, and definitely be cognizant of the fact that some forces may apply in both axes, and they may have separate components. Two things to consider is the difference between inertia and force. So if you throw a ball in deep space and it flies away with a constant velocity, its free body diagram would have no forces on it. Even though it's still moving away, it's doing so at a constant velocity, and there's no actual forces, even though it still has momentum. If you're throwing a ball vertically, if we forget about drag for a second, once you throw the ball and it leaves your hand, the only force acting on it is gravity. There's no force propelling it upward. That's merely its momentum or its inertia. And consider the difference between force and net force. So just because an object is still or moving at constant velocity doesn't mean that there are no forces on it. It just means the net force in that direction is zero. So for example, we have a book resting on a table. So if we were to look at this quickly, we're on Earth, we're assuming we're on Earth, so the force of gravity is present. And since it's just resting on the table, there's going to be a normal force pushing back from the table to the book to oppose gravity. And since it's just sitting there and not moving, there must be a normal, there must be no other forces present. So it's not like it's sliding, there's no friction, it's just sitting there, which means that we can express our free body diagram like this, with force of gravity pointing down, normal force pointing up, and we're in equilibrium. Okay, so we're going to try this system, and we're going to try doing a Zoom poll, and I'm going to launch this, and you're going to tell me whether the last few slides make sense, you're following along, or whether I need to go over anything again. So it should be popping up on your screen. Okay, so people who, okay, so it looks like about half people, about 70% of people are feeling pretty confident with it. Those of you who answered 2 or 3, if you have a question or a concern or something I could explain better, feel free to ask. That's what I'm here for. But if there are no specific questions on this last few slides, I'm going to continue. Okay, so there are 2 possible scenarios for any object with multiple forces acting on it. The net force in all directions, so x, y, z, is 0, meaning that it's in equilibrium, it's at constant velocity, or it's perfectly still. Or the net force in at least one direction is not 0, so it's accelerating. If we look at the first scenario, net force in all directions is 0. So like I said, this can mean either no velocity or constant velocity, so no acceleration, therefore no force, or no net force. So the sum of the contributing forces in each direction. So if you add up all the forces in the x direction, that's going to be 0. And if you add up all the forces in the y direction, that's also going to be 0. And z if that's relevant for your problem. So for example, let's say that there's a block being pushed at a constant velocity along a rough surface. If since at a constant velocity, we know that the net force in the x direction, since we're pushing it sideways, is going to be 0. It's not going up or down; it's staying in contact with the surface. So the net force in the y direction must also be 0. So if we're looking at the x direction, the pushing force is going to be exactly opposed by the frictional force, and the gravitational force pointing down is going to be exactly opposed by the normal force pushing up. Car with its parking brake engaged on the hill. There's a slightly more complicated problem with some tilted axes, which we'll get to in a few minutes. But essentially, the point is that the forces in the x and the y direction, they sum to 0. Lastly, skydiver at terminal velocity. With the terminal velocity, you have gravity pointing down, perfectly matched by drag pointing up. And so the velocity is constant. Okay, so let's say the other situation, the net force in at least one direction is not 0. So that means that we're accelerating in at least one direction. And in at least one axis, the forces aren't being balanced. So maybe you're pulling on something, but the object is accelerating as you're pulling on it. That means that your pulling force exceeds the frictional force, and therefore there's a net force pointing this way. And so if in that situation, we have to determine which axes, whether it's x, y, both, feature a net force. And then for each of those axes, which direction that net force is. Is it accelerating upward, downward, leftward, rightward, a combination? That's what we have to figure out if the net force is not 0. Okay, so I'm going to try this next poll. Okay, so how are we doing on the interpreting a free body diagram section? Okay. For those of you who are new, we were talking about free body diagrams. We're talking about the basics for how to create and interpret them. And we're going to get into some scenarios now. And my overall policy is, if you have a question, throw it in the chat so I can answer it right away before either of us forget what we're talking about. Okay. Seems like the majority of people are on board with this. I'm going to keep going. You back to the last slide. Which slide is that? Sorry, the chat wasn't loading for me.
Slide 11.
Slide 11. Let's see here. Can I go back? Slide 11, this one. Okay. Do you have a question about this one? Okay. All right. So we will continue. Let's go over some scenarios. The first one, a projectile. So this is pretty simple. You're throwing a tennis ball or a baseball. Projectile launched at an angle. So we can look at this ball at a particular point along its trajectory, as we've shown with this box right here. So if we count drag in this scenario, the only two forces acting here are drag and gravity. And to make it less confusing, we might, for our own, I guess, for it to make sense to us, we might draw the velocity with a dotted line just to remind us that the ball is moving in that direction, but it's no longer being propelled in that direction. It just has its momentum. So, but if you were asked, like, what should the free body diagram for this situation look like, and it asks you to include drag, then all you would see is gravity pointing down and drag opposing the direction of velocity. So technically, anything that isn't a force shouldn't be in a formal free body diagram. And in most cases, you'll find that drag is actually being ignored. They might just say neglect air resistance. And then in that case, the only net force you really care about is acting in the y direction, that being gravity, and it's in equilibrium for the x direction. Okay, let's look at a vertically launched projectile. So if you throw a ball perfectly straight up, which means that there's no movement in the x direction. So there's 2 points to be made here. One is more important than the other. So let's talk about the first one. If we count drag, then what we're going to see is that there are only 2 forces present, just like the other one. So we're noticing a pattern here. Projectiles tend to only be affected by drag and the force of gravity. The second thing to notice is, and this is a little bit more confusing, it definitely took me a while to get it first time too. You might notice that as it's going up, the measured acceleration downward, so how much it's slowing down as it goes up, is actually greater than the downward acceleration as it starts falling back down. And the reason for that is because as it's going up, since velocity is upward, the drag force is opposing velocity, so it's pointing down, which means that now your net force is force of drag plus force of gravity, giving you an overall higher acceleration downward, or negative acceleration. Whereas when it's on the way down, your net force is the force of gravity opposed to the force of drag. So since they're being subtracted instead of added together, that net downward force or net downward acceleration actually goes down when you're falling back down as compared to on the way up. Okay. Okay, let's do another check-in for the projectile section. And this is also a great time to ask any questions if you've got any. Okay, so this is a little more mixed. Seems like most people are able to follow along, which is good. If you're having trouble, again, no dumb questions. It's only dumb if you have a question and you don't ask it. So please ask if any of this is confusing. But since I'm not seeing any questions right now, I'm going to keep going. But if you want me to go back at all, can I please slow down a little bit? Okay, do you mean slowing down content-wise or slowing down talking? Because I realize that I talk too fast sometimes, but do you want me to slow down with the content or do you want me to slow down with my words? Oh, okay. Do you need me to go back to any of the slides? By the way, this presentation, yeah, like Sim said, we're going to send out the slides so don't feel obligated to. Okay, I'll go back to the last slide. Don't feel obligated to write down everything that I'm saying or everything that is on the slides, because you will get a chance to look back at this. Okay, so I'm going to continue then. Okay, so object on a ramp. So this is going to be something that you'll almost certainly encounter during your time studying for the MCAT or even on the MCAT itself. So let's say that we've got a box resting on a ramp or moving along it at constant velocity. So let's say it's resting on the ramp, not moving. So when we consider the free body diagram for this scenario, we're going to be noticing that there are three forces at work here. There's going to be our gravitational force pointing straight down, our normal force pointing perpendicular to the surface, and our frictional force, in this case static friction or Fs, pointing to oppose the potential. Okay, Trish, I'll get to your. I'm gonna finish the object on a ramp, and then I'm gonna go back to the projectile. So we have these three forces. Friction is going to be opposing the downward sliding along the ramp for this box. And this ramp scenario is actually kind of special because the best way to deal with it is actually to create a tilted axis system, like so. So what you do is you have your X direction going kind of parallel to the slope of the ramp, and then you have the Y direction going perpendicular to that, kind of off of the ramp and down into the ramp. And so that makes it really easy because then your normal force and your frictional force are going to be in the X-axis, or in the X and Y axis. And on top of that, your gravitational force, you can split that into its components and then include that in the Y and X axis accordingly. So notice here that the angle theta of the angle theta for the ramp is actually the same angle is actually present here between the normal force and a line perpendicular to the ramp and gravitational force. That angle right here is actually equivalent to this angle down here for the ramp. And so if you know what the incline of the ramp, is, then you can automatically split gravity into its components. So in the X direction, we have friction opposing F of G times sine of theta, and we have the normal force opposing F of G times cosine of theta. And so that way, we're able to then create our net force in the X and the Y direction. And since it's standing still, we know that frictional force equals Fg sine theta. They're just opposite signs. And F of n equals Fg times cosine theta. And they're opposite signs as well. And so this way we can, if we're given just the weight of the object and the angle, we can figure out what friction is, we can figure out what the normal force is. It's very easy once you have that information. So object on a ramp tilts the axes. That makes it much easier. Okay, so I'm gonna jump back to the projectile thing, and then I'm gonna check in with anybody who has a question about the ramp. So for the projectile, yeah, it's I noticed that Quan put in, why can't I access the chat? Let's see. Here it is. Okay. Yeah, so Quan pretty much got it. What essentially is happening is on the way up, gravity and drag are both pointed downwards. So it slows down really fast as it's going up, but on the way down, drag is actually pointing upward. So it's opposing gravity, which means that it actually lessens, it works against gravity. Therefore, that overall net force and net acceleration is actually lower in magnitude when it's falling back down compared to when it's going up. F of D stands for drag. All right, does that make sense? Awesome. All right, so let's check in about the object on a ramp with the tilted axes. I'm going to give you guys a poll to quick check in on that. Okay, it's looking like we're pretty comfortable with this. Let's see. Okay. All right, so the next scenario we're going to be talking about is elevators. So this can sometimes become important when we're talking about when there is a net force. So there's three possible scenarios for an elevator. The first one is that it's going up or down at a constant velocity, or it's just not moving. The second one is it's accelerating upward, so it's moving upward and getting faster, or it's decelerating downward, meaning it's going down, but it's getting slower. So in that second scenario, the acceleration and net force is pointed upward. On the other hand, if it's accelerating downward or getting faster as it goes down, and or if it's getting slower as it goes up, that net acceleration or net force is going downward. Are we clear on that? It kind of gets confusing, but any confusion on that? I'm going to assume that if nobody says anything, I can keep going. Okay. So our first scenario, constant velocity. If it's a constant velocity or if it's at rest, the net force is 0. Since we're only really working in the y direction here, we've got our two forces, tension, which is the cable holding the car and possibly an occupant up, and the force of gravity, the weight of the car, and if it's occupied, a person. And because the net force is 0, the tension force and the gravitational force are equal in magnitude, and therefore the net force is 0. In our second situation, accelerating upwards, so getting faster while going up, or decelerating downward, slowing down as it goes down, that means that there's a net acceleration pointing upward, and therefore a net force pointing upward as well. Since our only two forces are the tension force and the gravitational force, we know that the tension force must exceed or be greater than the gravitational force in order to produce a net force pointing upward. Similarly, if we're accelerating downward, or so moving down and getting faster, or decelerating upward, moving up and getting slower, that gives us a net acceleration pointing downward, which means that since tension and gravity are the forces that work here, the tension force must be less than the force of gravity. Gravity must exceed tension, giving us a net force pointed downward. Okay, so let's check in on this subject. How did that sound? Okay, it seems like its tension force is always facing up. In the case of the elevator, yes, tension force is always facing up since it's being held up by that cable. Okay, so it seems like we're pretty much on the same page for this. Yep, you're welcome. As always, keep asking questions if you have them. We'll continue on to our final scenario. Resume makes me conceptual. So we're kind of trying this out. So I think there's going to be a mix of going over concepts and going through questions. I have some practice questions that are conceptual at the end of this, but in the interest of not keeping you guys here for, I don't know, an hour or two, I think we're gonna kind of break up. We're gonna break up more instructional, like concept sort of things, and then practicing more application in terms of the MCAT questions. Okay, so yeah, Quan is right. Tension, yeah, tension is going to be just the force of pulling based on a rope or a wire, and it depends on what the situation is. But for an elevator, the tension will be pointing up. Will there be any questions based on things going on inside the body? Do you mean on the MCAT? Yeah, there tends to be some level of biophysics type of questions happening, like blood flow, muscles, that kind of stuff. So free body diagrams can be important there too, especially if you're talking about, like, I don't know, a muscle lifting. Yeah, it's probably going to be passage based when it comes to stuff going on inside the body. In these meetings, I don't have any planned right now for this meeting, but in future meetings, as we diversify what we're doing and the types of things we're going over, whether it's concepts, computation, passage interpretation, we'll definitely get into more of that sort of thing. Okay, cool. So let's look at our final type of conceptual scenario, that being dragging an object at an angle. So you've got your kid dragging a sled and they're pulling it with a rope at a particular angle. So if we think about this, we got, okay, which forces are involved? There's going to be a tension force in the rope. There's going to be a gravitational force on the object, a normal force opposing the gravitational force. Then there'll also be friction opposing the horizontal motion as it slides along the surface. So one thing that's important to realize is, so let's say we set our axes as y going up and down, x going left and right. We need a free body diagram to tell us what's actually happening. So we might think that normal force equals gravity. That's what we usually see with an object on a surface, right? But actually, that's not quite true. If we look at this, we see that in the x direction, we have kinetic friction. Yeah. In the x direction, we have kinetic friction. I'm recording this right now, actually. So we will, for people who, if you want to go back to this, we'll have this available if you want to listen again to the questions that were asked or the explanations. Okay, in the x direction, we have kinetic friction opposing motion, and then we have one component of the tension force, that the x component, that's pulling to the right, and that opposes friction. In the y direction, we have the normal force pointing up, we have gravitational force pointing down, and we also have another component of the tension force pointing up. So if we look carefully, gravity is balanced out by two forces, normal force and that bit of tension force that's in the y direction, which means that the normal force is actually less than the gravitational force, which we wouldn't necessarily have realized if we hadn't thought about it in terms of this free body diagram. In the x direction, it's a little bit simpler. We just have our x component of tension equaling our kinetic friction, since we know that the object is going at constant velocity. So there's equilibrium in the x direction and in the y direction. I don't think I included a check-in for this section, but any major questions about this section, just go ahead and put it in the chat. I'll give you a few seconds to do that. Yeah, and Quan is right. This type of conceptual topic session is going to be more about kind of getting familiar and comfortable with this type of analysis. And as you get more and more practice, this will become more and more second nature to you. And so you can look at a diagram and not really have to spend a ton of time drawing it out. So is the net force 0 for both directions? Yes, if we're going at a constant velocity, then the net force in the x direction is going to be 0. And since we're just sliding along a surface, it's not accelerating up or down, so the net force in the y direction is also going to be 0. That's why we can set these forces in each direction equal to each other. Okay, so I'm going to continue. We're going to quick talk about some common mistakes. Just checking the time here. Okay, so common mistakes. These are pretty by the numbers, and the MCAT will also expect you to make these mistakes, and they will give you answers that play into these mistakes. So the key is to avoid those answer choices. So first one is very common. It's assuming that an object in motion must have a force propelling it. So if you remember, we're throwing that tennis ball into the air. There is no force that is actually giving it that motion once it leaves our hand. The only thing that's happening is gravity and possibly drag is going to be slowing it down. And if we throw it straight up, gravity will be slowing it down. It's directly opposing. If we have a horizontally launched projectile, there's no force that's actually keeping it moving to the right, only its momentum. And gravity will just continue to pull it down until it hits the ground. Second one, assuming the net force is 0, just because you have forces that are acting in opposite directions doesn't mean that those forces necessarily add up to 0. The problem will tell you whether there's a constant velocity or whether it's standing still, or whether, in contrast to that, there is a net force at work, in which case you'll have to approach it a little bit differently. So don't assume necessarily that, oh, this force cancels out this force and this force cancels out this force, unless the situation is that way, meaning it's constant velocity or it's standing still. And this kind of ties into, this last one kind of ties into the dragging the sled along the ground problem we just looked at. Don't assume that normal force always opposes gravity and is equal to gravity. Normal force often is equal to gravity, but that assumes that there are no other forces in the y direction at work. So make sure when you're thinking about these situations that you always take into account all the forces or components of forces that are acting on a given axis. Okay, so this is the end of the content part of the presentation. I have some conceptual practice problems for us to go over, where I'm essentially just going to show you. We can show you the problem. We can kind of have a few seconds to think about it. You can ask any questions in the chat if you want to, and then we can talk about the answer. Before we do that, are there any questions on the overall presentation? Anything you'd like me to go back to or explain more clearly? I'll give you a few seconds to put that in the chat if you would like. Okay, hearing and seeing none, I'm going to continue to our practice problems. Okay, so our first one. A gymnast is holding onto a bar and is suspended motionless in midair. The bar is supported by 2 ropes attaching to the ceiling. Diagram the forces acting on the combination of gymnast and bar. So I'm going to give you a minute or two to try this out, and then we can go over the answer. Yeah, Quan brings up a good point. The forces of tension should point away from the mass in the direction of the rope. So it's like the rope is basically applying a pulling force on the object it's attached to, and that's tension. Okay, is there anyone who needs more time before we go over this one? Okay, so for this one, we're going to have the gravitational force pointing down on the gymnast and the bar, the mass of the gymnast and the bar, the weight of the gymnast and the bar pointing down. And then opposing that, we have the two tension forces. If the ropes are identical and at the same angle, then those tension forces are going to be equal to each other. But the main point is that there are two tension forces that together cancel out the force of gravity. So if the ropes are the same and force of gravity is 700 newtons, tension force in each rope will be 350, assuming, of course, that the ropes are the same and they're both vertical or at the same angle. Okay. If there are any questions, go ahead and put them in the chat. I'm going to keep going. All right. An egg is free falling from a nest in a tree. Neglect air resistance, so don't worry about drag. And diagram the forces acting on the egg as it's falling. I'll give you a minute to do that. Okay. All right. So it's a pretty simple diagram. It's just free falling, and since we don't care about drag, the only force that's actually showing up is gravity, and it's just going to be the force of gravity pulling it down. All right. A flying squirrel is gliding, meaning it's not flapping its wings, from a tree to the ground at constant velocity. Consider air resistance and diagram the forces acting on the squirrel. Okay, so let's go over this one. It's pretty straightforward. It's constant velocity, which means that we're at equilibrium. And since we're considering air resistance, we've got the F air or drag being equal and opposite to gravity, and that gives us a net force of 0. Yeah, so this is what the free body diagram would look like. All right, next one. A rightward force is applied to a book in order to move it across a desk with a rightward acceleration. The book is accelerating to the right. Consider frictional forces, neglect air resistance. Diagram the forces acting on the book. This is a little bit more complicated. All right. For this one, we've got equilibrium in the y direction. So it's just sliding across. So normal force and gravity are going to be equal and opposite. However, in the x direction, since we're accelerating to the right, our applied force is actually going to exceed the frictional force. So that arrow is a little bit longer than the frictional force. And so that tells us that there's a net force in the rightward direction, giving it a rightward acceleration, like it says in the problem. Okay, with this one, so it's a slight change. A rightward force is applied to a book in order to move it across a desk at constant velocity. Consider frictional forces, neglect air resistance. All right, so for this one, very similar to the last one, except this time it's at a constant velocity. So you have equilibrium in both the x and the y axes, which means that not only are normal force and gravity equal and opposite, but the applied force and the frictional force are also equal and opposite. All right, a college student rests a backpack upon his shoulder. The pack is suspended motionless by one strap from one shoulder. Diagram the vertical forces acting on the backpack. So just the vertical one. All right, so we're seeing so tension in this case is, you can kind of exchange that if you want to say like normal force on this, like on from the shoulder against the strap. This one's kind of a like, okay, let's consider the backpack as a rope like object. So you have tension pulling the backpack up, tension from the strap, and then you have gravity pulling the backpack down. And so that, since the backpack is not accelerating upward or downward, it's going to be an equal and opposite. These two are equal and opposite forces, and it's an equilibrium. Okay. A force is applied to the right to drag a sled across loosely packed snow with a rightward acceleration. Neglect air resistance. All right, so here we've got normal force and gravitational force opposing each other, and since it's not going upward or downward it's not accelerating upward or downward, we have equilibrium in the y direction. In the x direction, we have frictional force, but we have a applied force that is stronger in larger magnitude than the frictional force, and accelerating to the right. And so there's a net force and a net acceleration toward the right. Last couple problems. A football is moving upwards towards its peak after having been booted by the punter. Neglect air resistance. Diagram of the forces acting upon the football as it rises upward toward its peak. All right, so this is our basic projectile question. So as it's going upward, the only force acting on it is gravity. There's no force propelling it upward once it has left the boot of the foot of the punter. The car is coasting to the right and slowing down. Neglect air resistance. All right, for this one, we're going to see normal force and gravity, as always, since it's on the surface, that being the ground. It's not accelerating upward or downward, so the net force in the y direction is 0. So normal force and gravity are equal in magnitude. There is no force propelling the car to the right since it's just coasting, but since it's slowing down, we know that there's a frictional force acting against that motion. So therefore, the frictional force is pointed to the left, and there's that net force pointed to the left. I think that's the last problem. Yes. Okay. So before we talk about other stuff, briefly, are there any overall questions about free body diagrams or anything we've talked about today? Anything you'd like me to go over again? I didn't explain clearly enough. Any of that? Now is the time. Yeah. Also, if you have no questions, go ahead and say you don't have any questions, just so I know you're still with us. Okay, I'm assuming. Okay. Okay, so I'm not seeing any questions yet. I'll still be watching the chat for questions if any come up in the next couple minutes. But we're going to talk about something more general related to what we're doing here. So these sessions are going to be free, and it's a part of our effort to make MCAT content and MCAT knowledge and the ability to ask and answer questions accessible to anyone who's taking the MCAT. And so we have started a GoFundMe to help us cover some costs associated with the website, advertising, etc. Since most of the work that we do is free, please consider donating. Even if you put in like a couple bucks, like if you guys like $1 per session or something like that, as you're able to, that can make a difference. It all adds up. Yeah. So, and lastly, please go ahead and so Sim just put the link in the chat. It's also going to be in the slides that we send out and in the newsletter. And also please share if you found this helpful. Please go ahead and share what we're doing and the newsletter with your MCAT study buddies, anybody you know who's taking the MCAT and could benefit from what we're doing. We'll also, since this is our very first session, we're super open to suggestions, questions, concerns, criticism, praise, if you'd like. And so we'll definitely be reaching out to you to ask you kind of what you thought of this overall session, how we've run it, and what we could do differently in the future. So that's all I've got for today. Thanks to all of you who were able to come. I hope it was helpful. Sim, do you have anything you want to add? Any housekeeping stuff? You can unmute yourself if you want.
Yeah.
Go ahead.
Thank you everyone for coming out tonight, and to Nitij for leading our first topic session today. And we're actually going to be having another one and on Wednesday for cars, and I'll be leading that one. So if you haven't signed up and you want to, I'll also send out a link in another email coming out soon. And if you have any questions, you can reply to that. Yeah, but that is all I have.
All right. With that, then I'm going to go ahead and stop the recording, close this meeting. Thank you all for coming. Feel free to email us at mcatquestions@gmail.com if you have any questions.